Welcome everyone. In this video, we're going to start to look more at the structure of how everything fits together in linear algebra. We've seen vectors, we've seen matrices, we've learned how to multiply matrices, and now we're going to start to see what this does for us. So to start with, suppose I have a matrix, which is an n by m shape. So this means it has n rows and it has m columns. Now, if I have such a matrix, and I have a vector, which is a column vector, so it's m by 1, then I can consider the product of this matrix times this vector. So I can consider A times that vector v, and this will be something which is now an n by 1 column vector, so a column vector with n entries. So sending v to A times v defines for me a function which goes from, it takes as input an m-dimensional vector, and it produces as output an n-dimensional vector. And I'm going to call this function f sub a. So f sub a of a vector v is simply a times that vector v. Right, this is a function defined by a matrix. Now, the inputs here live in Rm. We call this the domain of this function. And the outputs live in this r to the n. So we call this the co-domain, because mathematicians aren't very imaginative. And if we need another word, we just take a word we already have and stick something like a co in front of it. So we've got a function here. Now let's look at this function. This has a very important property which really makes life easy for us. And this important property is the following. If I look at f sub a of lambda 1 times v1 plus lambda 2 times v2. So I'm going to take this function and apply it to a linear combination. What I get is the corresponding linear combination of the outputs. I get lambda 1 times f sub a of the first vector plus the second coefficient, lambda 2, times the function evaluated on the second vector. So f sub a preserves linear combinations. This is a super, super important and useful fact. Why is this? What's the reason behind this? Well, you go back to the way matrix multiplication was defined. So if we have our A matrix, and it has, I'm going to think of it as a stack of rows, and we've got our V vector, and I'm going to think of this as a column vector, then when I look at the output, I get a column vector, and the ith entry here is given by taking the ith row and dotting it with the v vector. So let's call this ith row a sub I. So the ith entry here is ai as a vector dot product with v. And this fact that this function we're defining preserves linear combinations comes from the fact that dot products preserve linear combinations. And you can very easily check that just by writing it out. So understanding how matrix multiplication works gives us this understanding of something very special that these maps defined by matrix multiplication, this very special property of them. Let's look at an example. So I'm going to take my matrix A to be 0, 1, 1, 1, 5, 6. So there's my matrix. So this is a matrix that has 2 rows and 3 columns. So it is a 2 by 3 shaped matrix. So this defines a function f sub a, which goes from R3 to R2. So it takes as input a column vector of length 3 and produces as output a column vector of length 2. So let's see what it does to an arbitrary vector, f sub a of x, y, z. So there's some arbitrary vector. This is going to be equal to this matrix times this vector. So this is 0, 1, 5, 1, 1, 6 times x, y, z. And I can multiply this out. I get 0 times x plus 1 times y plus 5 times z in the first component. 0 times x plus 1 times y plus 5 times z in the first component. And 1 times x, 1 times y, 6 times z. 1 times x plus 1 times y plus 6 times z in the second component. Okay, so that's what I get from just doing matrix multiplication. Now I can also use the observation from the video where we learned about the structure of matrix multiplication that says matrix times a vector means use these coefficients to make a linear combination of the columns. So this should also be equal to x as a scalar times the vector 0, 1, the first column, plus y as a scalar times the second column, so that's 1, 1, plus z as a scalar times the third column, 5, 6. And if you check, you add these 3 up, you get exactly this matrix here. Now, we can do one more thing. We can use the fact that this is a linear transformation, and note that x, y, z is equal to x times the vector 1, 0, 0, plus y times the vector 0, 1, 0, plus z times the vector 0, 0, 1. So I'm just observing that I can take an arbitrary vector and write it as a linear combination of these 3 standard basis vectors. So I'm just writing my vector as a linear combination of the standard basis vectors. And now I'm going to use the linearity fact to say that f sub a of x, y, z, this is a linear combination here, so applying f preserves this. This is equal to x times f sub a of this first vector, 1, 0, 0, plus y times f sub a of the second vector, 0, 1, 0, plus z times f sub a of the third vector, 0, 0, 1. And this is using linearity. The fact that f sub a preserves linear combinations. And now I can work out what is each one of these 3 vectors. Well, f sub a times this vector, 1, 0, 0, will be a couple of ways to see this. You can either multiply the matrix by this vector, or you can say, this means take 1 times the first column, 0 times the second column, 0 times the third column. So this is the first column of A. F sub A times 0, 1, 0 is the second column. And so on. So we haven't learned anything new. We've just seen the same calculation in sort of 3 different ways. And it all fits together perfectly. Everything is equal. You get the same answer no matter which way around you look at this. Let's look at some more examples now. Next example. Let's consider the function f of x, y. So rather than give you the matrix, I'm going to give you the function here. And this is going to be given by the following formula. First component is going to be 3x plus 7y. And the second component will be 2x minus y. So this is a function from R2 to R2. So it has two-dimensional vectors as its domain and two-dimensional vectors as its codomain. So this is some function. I've just written down a formula for it. This function is linear. And in fact, it's equal to multiplying the matrix A times the vector xy, where our matrix A is given by 3, 2, 7, and minus 1. So the 3 from that x coefficient, the 7 from that y coefficient, the 2 from that x coefficient, and the minus 1 from this minus y. So I've just written down these numbers because I'm experienced with doing this translation. But if you don't believe me, go ahead and multiply this matrix by this vector, and you'll see that you'll get exactly the same answer. Let's consider another example here. How about f that takes a column vector as input and produces just a single number as output? So I'll just write x squared, or you can think of this as a number or as a vector of length 1. So this is a function going from R2 to R. What sort of function is this? Well, this is not linear. Why is this not linear? Well, let's see what happens when I take a very simple linear combination, a scalar multiple. So f of 2x, 2y. So I'm just multiplying the input by a factor of 2. What I'm going to get out is 2x squared. So I'm taking, the function takes the first input and squares it, and that's the output. So if I multiply the input by a factor of 2, now I'm going to take the first component and square it. So I get 2x squared, which is 4 times x squared, which is not equal to 2 times f of xy. So because that's not equal, we have not preserved this linear combination, which is 2 times the vector xy. So this is not a linear map. So that's one way a function can be not linear. It can have some terms which are not just a sum of numbers times x's and y's, or x's and y's and z's, but if you see some x squareds or y cubes or an x times y, if you see something which is a polynomial of degree greater than 1, then the function you're looking at is not linear. One more example of a way something can fail to be linear. Let's consider the function f that goes from R3 to R2, given by f of x, y, z is equal to 0, 1. This function is also not linear. And the reason is, well, just check whether it preserves a linear combination or not. So f of x, y, z plus, let's take the 0 vector, 0, 0, 0. Well, when I add the 0 vector to anything, this is f of x, y, z. Adding the 0 vector doesn't change any vector. And the output of this is 0, 1. On the other hand, f of x, y, z plus f of 0, 0, 0 is 0, 1 plus another copy of 0, 1, which is 0, 2. And these are not equal to each other, so this function is not linear. So I want to put this this observation about linearity to use here, let's suppose that we have a vector, I'll call it v, and the components will be v1, v2, up to vn. And I can write this as a linear combination of the standard basis vectors. So I can write this as v1 times b1 plus v2 times b2, dot, 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 up to vn times bn, where bi is the vector that has 0, 0, dot, dot, dot. It's got a 1 in the ith position, and then zeros everywhere else. So b1 is 1, 0, 0, 0, 0, 0, 0. b2 is a 0, and then a 1, and then all zeros, and so on. So this is the standard basis. Any vector can be written in this very simple way in the standard basis. And if f is some linear transformation, then f of v I can write as v1 times f of the first standard basis vector plus v2 times f of the second standard basis vector, and so on up to vn times f of the last standard basis vector. So we have two very important observations from this. They're important enough that I'm going to write them in a different color here. First observation is knowing what a linear function f does to these standard basis vectors determines completely what it does to any vector. So all I need to do is compute f of b1, f of b2, and so on. I get a list of n outputs from this function. And from that list, I can then immediately, using this formula, tell you what this linear function does to any vector v at all. So that's a very useful fact. And the second fact here is if we set A to be the matrix, so this is going to be a matrix that has a number of columns equal to n. And we're going to set it to be the matrix where the first column is f of the first standard basis vector, and the second column is f of the second standard basis vector, and so on. And the last column is f of the last standard basis vector. So we have n columns here. If I create this matrix from the output of this linear function on the standard basis vectors, then plugging into this formula here, we see that the function associated to this matrix is exactly the linear map that we started with. So any linear function is a matrix, basically. The only linear functions we can write down are the ones that come from multiplying by a matrix. Right? Every linear function uniquely corresponds to a matrix, and every matrix gives us a linear function. So they're the same thing, linear functions and matrices. And this is part of why matrices are so important. Let's look at a couple of examples of finding the matrix associated to a linear transformation. So here's the first one. Let's take the function f, which takes an x and a y as input and produces as output the following vector, 3x plus 7y, 2x minus y. I think this is a matrix I used earlier. So we want to find what is the matrix for this. So we need to evaluate this on the two standard basis vectors. We are taking two-dimensional inputs, so we've got two different standard basis vectors we need to use. So f of 1, 0 I'm going to plug in x equals 1 and y equals 0. So I get 3 plus 0, 2 plus 0. So I get 3, 2, and f of 0, 1. So now I'm plugging in x equals 0 and y equals 1. So I get 7 and minus 1. So this one gives me its first standard basis vector. So this is the first column of my A matrix, 3, 2. And the second column is this vector. So this is 7, minus 1. So there I've worked out what the matrix is for this. So the linear transformation f sub a of v is equal to this function f on some vector v. And this is to say a times v equals f of v. OK, that's the first example. Let's do a second example that's a little bit more geometric rather than algebraic. So let's consider now a function f that goes from R2 to R2. And I'm going to tell you a geometric recipe to define this function. This is going to be anti-clockwise rotation by 90 degrees. OK, so let's draw a picture of what's going on here. Here are my two standard basis vectors. So this is basis vector 1 is 1, 0, and basis vector 2 is 0, 1. And what happens when I rotate these by 90 degrees anti-clockwise? So this one's going to come up to here, and this one's going to come down to here. And so these two will go and end up in this position. This point over here is minus 1, 0. So writing that out, f of b1 is b2, which is 0, 1. And f of b2 is this minus b1, minus 1, 0. So the matrix A, in this case, the matrix that represents this anti-clockwise rotation, is given by 0, 1, and then minus 1, 0. So multiplying by this matrix A implements anti-clockwise rotation by 90 degrees. If you want to work out the matrix for any other rotation by whatever other angle you want, same idea. And we can use this also to work out what are rotations in 3 or more dimensions. So this is a very useful approach. One last topic I want to look at with this idea of the relationship between matrices and linear maps. We can compose functions. So if I have a function that goes from, let's say, R L to an R M, and let's call this f. And let's suppose that we have another function g that goes from Rm to Rn. Then I can look at the composition function here, which is g composed with f. So this is the function which sends a vector v in this domain R to the L here to, this is going to be g of f of v. So that's what that little circle means, composing these two functions. Right. So this, so far, is something we can talk about for any two functions. But now, if these two functions are linear, so if f and g are linear, so f is equal to the transformation associated with some matrix A, and g is the transformation associated with some matrix B, then, well, we know that f sub A of v is just multiplied by this matrix A, and we know that g of some vector w which is f sub b of w, is multiplied by b. So when we compose these two, where we do first the A matrix and then the B matrix, or first the f function and then the g function, so this is g of f of some input vector v, this is equal to the B matrix times the A matrix times my input vector v. Now, matrix multiplication is associative, so I didn't need to write these parentheses. I can just write this as B times A times V, or I could put the parentheses in a different way. And this is equal to the linear transformation associated to the product of these two matrices applied to the vector V. And so the punchline of this is composing linear maps corresponds to matrix multiplication. So what I mean by that is if I have f sub b composed with f sub a, this is equal to f of the matrix B times the matrix A. Thank you very much. That's the end of that video. Hello everyone. Welcome to this video where we're going to take a little bit of a closer look at the anatomy of linear transformations, all the different parts and some of the names we attach to various properties of these things. So the setup here is we have a matrix which is going to be n by m. And this represents for us a linear transformation, f sub a, which goes from Rm to Rn, and this is the function which sends a vector v to a times that column vector v. So as I mentioned in the previous video, the source of the inputs here is what's called the domain of this function, and where the outputs live is called the codomain. And now we've got a little bit more I want to talk about. There is the image of this function. So the image, or it's sometimes called the range, two different words that people use in different contexts for exactly the same thing. The image is the set of all possible outputs. So it's, in slightly more precise mathematical terms, it's the set of all vectors of the form A times V, where V is a vector in the domain. Now, another way to think about this is when I do A times vector V, this says use the components of V to make a linear combination of the columns of A. And so as I vary the vector V, what I get in this set is all possible linear combinations of the columns of A. So I get exactly the span of the column vectors of A. And all of this is a subset of the codomain. Now, this is a span of a bunch of vectors, so it's automatically a linear subspace. And a linear subspace has something called a dimension. So the dimension, remember, is the smallest possible number of vectors we need to span it. So another way of thinking of it, of the dimension, is it's the number of linearly independent columns of A. So the dimension of the image is the number of linearly independent columns of A. So if you look at the set of columns, they might be linearly dependent, in which case you find one that you can throw out without changing the span, one that's in the span of the others, and you remove that one, and you keep on doing this until what you're left with is no longer a linearly dependent set. It's now linearly independent. And so you've constructed something which spans the image and is linearly independent, so you've got now a basis for the image of this matrix, and you count how many vectors you have there, and that is the dimension of the image. And this has a name. We call this the rank of the matrix A. So the rank is just the dimension of the image, which can be calculated by saying how many linearly independent columns can you find in that matrix. Now let's look at a couple of examples. Let's look at some examples here. So if my matrix A is 1, 0, 0, and then 0, 1, 0, what is the image here? So we're going to look at all possible vectors we can get as output of this. So let's say I do A times some arbitrary vector AB. So this is a 3 by 2 matrix. So it takes as input a length 2 vector and produces as output a length 3 column vector. And this will be equal to, let's see, this will be equal to A times 1, 0, 0 plus B times 0, 1, 0, which is simply that. Okay, so what we see is the image is the xy plane inside R3. I can have any value for the first component, any value for the second component, and the third component has to always be 0. So if my x-axis is going that way, my y-axis is going that way, and my z-axis is going that way, then it's this plane back here, which is perpendicular to the z-axis. So the xy plane, it's everything where the z-coordinate is equal to 0. Okay, let's try another example. What if instead I change my matrix a little bit? So now it's 1, 1, 0, and then 0, 0, 1. In this case, so the image is the column span. It's the span of these two vectors. So it's everything I can get by walking either along the z-axis or along this vector, which points a little bit in the x direction and a little bit in the y direction. So let's try to draw a 3D picture of this. Here is my x-axis. Here's my y-axis. And the z-axis is perpendicular to the board here. So what I'm allowed to do is walk either along the z-axis or along this diagonal vector here, which is in the xy plane. And so what I'm going to get is kind of a plane which is making a 45-degree angle with the xz plane. So let's see if I can sketch this here. Something like that. So that's a 45-degree angle there. All right, so it cuts through the xz plane right along the z-axis. Let's try one more example. Let's suppose that my matrix A is some tiny little matrix. Let's just do 1, 2. So this is a 2 by 1 matrix. So the associated linear map here goes from R1, which we just call R, to R2. And the image is the span of this one vector here. So this vector, 1, 2, is 1 in the x direction and 2 in the y direction. So that's my vector that we're taking the span of. And so the span of that will be the line along that direction. So those are some examples of describing or computing the span of the columns or the image of a matrix. Now, linear transformations have a little bit more anatomy that I want to talk about. The other part of linear transformation that I want to talk about is the kernel. So if we have this linear transformation associated to a matrix A, and this is going from Rm to Rn, sometimes we want to know, it's a very important question, when does the input give us the 0 vector as the output? So we write this as kernel of this linear transformation. This is called the kernel or the null space. And what is it? It's the set of all input vectors v such that f of v is the 0 vector. So let's think about how to interpret that. This is equal to, another way to think about this is the output is a linear combination of the columns of A. So we're looking at the set of all possible ways we can take a linear combination of the columns to get the 0 vector. So this is the set of all linear combinations of the columns that give the 0 vector, the set of all coefficients that give the 0 vector as a linear combination of the columns. And another way to say that, I used this term in a previous video, is this is the set of all linear relations among the columns. So let's look at a very simple example here. If I have a matrix A, let's say this is 1, 2, 2, 4. You can just look at this matrix and say, the second column is 2 times the first. So this is a linear relation. We could say, if this is A1 and A2 are those 2 column vectors, I could say this is A2 is 2 times A1, or I could put it all onto the same side and say 2 times A1 minus A2 is the 0 vector of length 2 here. OK, so this is an example of a very simple linear relation among the columns. And this linear relation tells me that if I read off the coefficients here, this tells me that the vector 2 minus 1 is in the kernel. Now I can take this linear relation and I can multiply it by any number lambda that I want. And lambda times the 0 vector is still the 0 vector. So any number times this thing is also in the kernel of this matrix A. So what we've shown here is that the span of this vector is exactly the kernel. So the kernel is equal to the span of the vector 2, minus 1. In fact, this is one independent vector. Any set of vectors of size 1 is a linearly independent set. So this vector is a basis for the kernel. So taking this observation and generalizing it, note that the kernel of a matrix is always a linear subspace of the domain. Just as the image is a linear subspace of the codomain, the kernel is a linear subspace of the domain. So we have the kernel is a linear subspace of the domain, and we have the image inside the codomain. So associated to any linear transformation, you have these 4 different linear spaces, these 4 different vector spaces: the domain, the codomain, the kernel, and the image. Right. The last thing I want to tell you about here is a super important result called the rank nullity theorem. Right, the rank nullity theorem says if we have a linear map F going from Rm to Rn, so this corresponds to some matrix, but I won't bother writing down the matrix, then the dimension of the image, which is called the rank of this linear transformation, or the associated matrix, is equal to the dimension of the domain. In this case, that would be this M here, minus the dimension of the kernel. This has a name too. This is what's called the nullity. So the dimension of the image is equal to the dimension of the domain minus the dimension of the kernel. I'm not going to prove this for you. That'd be more for a pure mathematics module. But I can explain the idea here. The kernel measures measures how much stuff is getting crunched down. So for instance, if I have a map, let's schematically draw the domain Rm as one direction and a second direction. And these 2 axes that I've drawn here might stand for an R7 and an R3 or something like that. And so let's imagine that this linear transformation F is going in 2 steps. The first step is it's going to collapse everything vertically. So I'm going to project down onto this horizontal plane here. And then the second step is going to be map this thing into the codomain somehow. So maybe if there's the origin, this thing gets mapped like that. So the kernel is how many dimensions we're losing when we do the crunching down phase. And then the image is a copy of what we're left over with after we compress the kernel down to nothing. So here's the dimension of the domain, this M here. We crunch the dimension down by a number of dimensions equal to the kernel. So we've lost however many dimensions were in the kernel. This vertical bit here is the kernel direction. So we've lost however many dimensions we had in the kernel. We've lost a nullity number of dimensions. And then this thing includes, it embeds into here. And so the dimension of the image, what we see here, is the dimension of the domain minus how much we've lost when we collapse the kernel down. So that's where this rank nullity theorem comes from. Let's see if we can work out a simple example here. let's suppose that we're looking at, let's look at this matrix A, 1, 2, 2, 4 that we had from the previous example. So we're looking at a map from R2 to R2. And what we saw is that the kernel was spanned by the vector 2, 1, 2 minus 1. So 2 times the first column minus 1 times the second column gives me a 0. And anything else in the kernel is a scalar multiple of this vector. So the nullity is equal to exactly 1. So that's the dimension of the kernel. And the domain, our M here, was 2. So this is a map from R2 to R2. And so when we plug this into the rank nullity, this is the dimension of the image has to be equal to the dimension of the domain, that's 2, minus the nullity, which is 1. So the dimension of the image has to be 1. And in fact, the image is spanned by either one of those two columns. So the image is the span of that one vector. So indeed, the image has dimension 1. So it works out. It's a miracle. Great. That's the end of that video. Hello everyone. Welcome to this video where we're going to look at something much more pedestrian now. We're going to look at solving systems of linear equations. So this is coming way back down to earth. Instead of talking about abstract stuff like rank nullity, let's suppose we're in a situation where we've got some system of equations, like say 7x plus 6y equals 3, and 2x plus y equals 1. So there's a system of linear equations. And I can convert this into a matrix equation that says 7, 2, 6, 1 times an unknown vector x, y is equal to my right-hand side vector 3, 1. So this is something of the form matrix times vector equals vector. So the matrix and the vector, these are given. We've got numbers there. And the x here is the unknown. So we want to solve for x. OK, so that's the basic setup. Now let's think about what's involved in solving for x. Well, first of all, a times x, whatever this is going to be something in the image of a. So for this to have a solution, we'd better have that v is in the image. If v is not in the image, then there's no hope of having a solution. So v is in the image tells us that the same thing as saying v is in the span of the columns. So v is in the image is the same thing as v is in span of the columns is the same thing as saying there exists at least one solution. There might be more. This backwards E symbol here, I can't remember if I've used that already. We say, that's a mathematical shorthand for there exists. OK. Now, we've got a condition here that tells us whether or not there's any hope of finding a solution. But sometimes it can be the case that there's more than one solution. Let's look at what controls that. So if I have some vector w, which is in the kernel of this matrix A, so remember that means that A times w is the 0 vector. And let's suppose that we have, I'll call it x naught, is a solution. So when I write x vector, that's the unknown vector, and this thing x naught is some particular solution to this equation. So if I've got some solution, then so is x naught plus this w vector. Right? If I've got any one solution, I can add something in the kernel to it and get another solution. Let's see why that is. So A times x naught plus w is equal to, using the fact that this is linear, I can write this as A times x naught plus A times the w vector. This one here is my right-hand side vector v, because I've assumed that x naught is a solution. And this one here is the 0 vector. And when I add those together, I get my right-hand side vector v. So given any solution, I can make more solutions by adding things in the kernel. So this tells me, and in fact, this is all you can do to get more solutions. So the space of solutions is always given by finding one solution and then adding vectors in the kernel. All solutions are of this form. So that's a mathematical fact. That's a proposition or a theorem that I'm not going to give you the proof of, but it's not too hard to prove. Okay, so as soon as we find one solution, we can make lots more if we have lots more vectors in the kernel. So I want to erase this and give you a kind of flow chart or decision tree that tells you about how many solutions you might hope to find for some arbitrary system of linear equations. Okay, let's look at the decision flowchart for solving an equation of the form matrix times unknown vector x equals some right-hand side vector v. So the first question is the right-hand side vector contained in the image of A? The image of A is the column span of A. So two possibilities here. Either no or yes. If the answer is no, then we've got no solutions at all. If the answer is yes, then we have at least one solution. And we can do a little bit better and say, what is the dimension of the kernel? Remember, the dimension of the kernel is equal to the nullity. And if this is equal to 0, then we have exactly one solution. There's one and only one solution to this equation, no matter what right-hand side vector v that I choose, as long as v is in the column space. On the other hand, if the nullity is greater than or equal to 1, then we have infinitely many solutions. And these solutions are all of the form find one solution, some x naught, and then add to it some vector w, where w is in the kernel subspace. And this gives us all of the solutions. So if the kernel is dimension bigger than or equal to 1, then there are infinitely many vectors in the kernel. That's a vector there. And so I can make infinitely many vectors of this form, so I have infinitely many solutions. If the kernel has dimension 0 means it just consists of the 0 vector and nothing more. So when I take any one solution, the only vector in the kernel that I can add to it to make more solutions is the 0 vector, but adding the 0 vector doesn't change anything. So if I found one solution, all I've got is that one solution, and that's why we have exactly one solution when the kernel has dimension 0. So there's the flowchart for solving equations. Now, let's look at a little bit of an example of the method for solving these things. So this is something that probably many of you have seen before. How do we actually solve an equation? Let's look at an example of solving a system of equations. So I've got a system here. Let's suppose we're going to look at 2x plus 3y equals 4, and 6x plus 4y equals 9. So there's a system of two equations, two unknowns. So the procedure that we're going to do if we do this by hand is what I'm about to go through. In practice, of course, you don't solve these things by hand. You hand it to a computer, and the computer runs an algorithm, which computers are very good at doing, and spits out the answer very quickly. But it's a good idea to understand what that algorithm is, and so it's worth going through solving these things by hand at least a few times. So the first step is we're going to choose one of the variables. Let's choose x. And we're going to eliminate x from, let me call the equations 1 and 2. I'm going to eliminate x from equation 2. So the way I do that is I take equation 2, and I'm going to subtract 3 times equation 1. And what this gives me is 6x minus 3 times 2x plus 4y minus 3 times 3y equals 9 minus 3 times 4. So these two here cancel out. That gives me a 0. Here I get 4 minus 9y, so this is a minus 5y equals 9 minus 12, that's a minus 3. So y is 3 divided by 5. Okay, so that's half of my solution. I found out what y has to be. And then we're going to substitute what we just found here back into equation 1. So we substitute this back in. We have 2 times x plus 3 times what I found out y has to be, which is 3/5 equals 4. And if you run through these numbers here, I'll just cut to the chase. This gives us x equals 29 over 10, assuming I haven't made a mistake doing the arithmetic in my head there. Okay, so xy equals, whoops, I'll just scribble that out, 29 over 10 and 3 over 5. So there's our solution. Right. So there were two steps. We did this elimination step, and then we did this back substitution step. And so the general algorithm called Gaussian elimination that the computer will usually use when you tell it to solve a system of equations is a generalization of this two-step process. First, it does a bunch of eliminations, and then it does a bunch of back substitutions. If you want, you can read about Gaussian elimination and how it works, but you don't need to know the details of that to get the idea that when a computer solves a system, it's doing exactly what you do here by hand. Right. The way I've set up this system of equations we were a little bit lucky in that I chose a system where this right-hand side vector was indeed in the column space of the matrix. And we'll talk more about why this worked out so nicely. But if you're in a situation where instead of a unique solution, there is more than one solution or less than one, so there's 0 solutions, then this process would go a bit haywire at some point. If there are no solutions, what you're going to find is that at some point you can't satisfy all of your equations. And if there are infinitely many solutions, what you'll find is that you can just completely eliminate one variable from the equations, and then you can't find out what value that variable has to be, but you'll find out what all the other variables have to be in terms of that one. And so you have at least 1 degree of freedom, or if the solution space has dimension 2 or 3 or 4, you'll have some number of variables that you can't determine, and those are called the free variables, and then you determine all the rest of the variables in terms of those. Right. So that's the general process for solving these things. So the last thing I want to emphasize is solving an equation, ax equals v. What this means, we're solving for this variable x, means finding a linear combination of the columns of A to give v. So always keep this in mind. Solving systems of linear equations means finding linear combinations that give some prescribed vector. Right. Thank you for listening. Hello, everyone. In this video, we're going to look at inverses of linear transformations. So going back to calculus and functions, we've seen things like when f of x was the exponential function, e to the x. Then there's an inverse function, g of x, which was the log of x. And so if I did f composed with g of some input x, I got that input back again. And we've seen other examples of this, like if you've done any trigonometry, we've got the sine and cosine functions, and then as long as you restrict the domain to the right kind of interval, then you've got the arc cosine, or sine inverse, and cosine inverse, and you've got the arc sine, sine inverse, and the arc tangent function. So we've seen lots of examples of a function and the inverse function, x squared and square root of x. Here's another example, x cubed and cube root of x. So I want to think about, in this video, what can we say about inverses to functions when the functions we're talking about are not single variable functions from R to R, but linear functions from some vector space Rm to some vector space Rn. What can we say in the case where it's a linear function like this? Well, to start with, let's take a very special matrix and a very special linear function. The matrix is called the identity matrix, and it comes in various sizes. So I'll write I sub n. Sometimes people use other notation for this, but this is the matrix that's 1, and then a lot of zeros, 0, 1, and then a lot of zeros, 0, 0, 1, and then a lot of zeros, 0, 0, 0, 1, and then a lot of zeros. So it's 0 everywhere except down the diagonal where we have 1s. So this is what we call the n by n identity matrix. Obviously, you can make one of these of any shape you want as long as it's a square matrix. So it doesn't make sense to talk about the identity matrix if it's 3 by 7. But if it's 3 by 3 or 7 by 7, then we can. Now this identity matrix has a special property. If I have any matrix A, and let's say this is an n by m matrix, the special property says the identity matrix of size n, so this is an n by n matrix, times my matrix A, which is n by m. Well, the output of this, remember these internal dimensions match, and so the output is an n by m. So the output is the same shape as A, and if you calculate it, what you get is actually the matrix A again. And similarly, if I take my matrix A and I multiply it by a square identity matrix, now I'm putting that on the right side, so it's got to be m by m instead of n by n, I also get back my matrix A. So the very special property of these identity matrices, multiplying by them does nothing. So what this is saying is that the linear function associated to the n by n identity matrix, so this is a function from Rn to Rn, this is the linear function that does nothing. This sends some vector x to that same vector x. It does absolutely nothing. It takes an input and just hands you back that same input and calls it the output now. It's a lazy function. OK, let's zoom in to the special case where our matrix A that we're looking at is a square matrix. So it's an n by n matrix now. And this means that the associated linear function goes from Rn to a vector space of exactly the same size. Now, let's think about this for a moment. If the dimension of the kernel, this is the nullity of this matrix, or this linear map, is equal to 0, this says the columns of A are linearly independent. If the columns are linearly independent, we've got rank nullity. This rank nullity theorem tells us that the rank of this matrix A is equal to the dimension of the codomain, which is n here. But the dimension of the codomain, of the domain, is equal to the dimension of the codomain. So, so the image has dimension equal to the codomain. Normally, the image sits inside the codomain here. Here we're in a situation where the dimension of the image is n and the dimension of the codomain is n. And the only way you can have an n-dimensional thing sitting inside an n-dimensional thing is if it's the whole thing. So we've got the kernel is just the 0 vector. The kernel is 0-dimensional, and the image is everything. So in this situation, f is what we call injective and surjective, or bijective. It's a one-to-one and onto mapping from Rn to Rn. So this is what we need for an inverse function to exist. So we can call this f inverse. And this is the function which sends a vector v to the vector x such that ax is equal to v. So f inverse takes a right-hand side vector v, and it gives us as output the solution to this equation. Now note that this f inverse function here is linear. This is a linear function. So f inverse is equal to f sub b for some n by n matrix B. Because every linear transformation is given by a matrix. OK, now since this is the inverse function to my original f sub a, right, f inverse composed with fa equals the identity, I'll write it as id, and similarly fa composed with f inverse is the identity. But f inverse is f sub b, so I can rewrite these two conditions here as f sub b composed with f sub a is the identity, which, by the way, is the linear map corresponding to the identity matrix. And this is also the linear transformation corresponding to the product of these two matrices. And similarly, we have fa times b is equal to the identity matrix. So this matrix B, we call it A inverse. It's the inverse matrix to A, and it's a matrix such that A times the inverse is equal to A inverse times A is equal to the n by n identity matrix. So if we have a square matrix and the dimension of the kernel is 0, then we have an inverse function, and that inverse function corresponds to an inverse matrix. So we can find an inverse matrix. So solving a system of linear equations corresponds to trying to find an inverse to your square matrix, which you can do as long as the kernel has dimension 0. So if this inverse exists, we say that A is an invertible matrix, or it's an invertible linear transformation. OK, let's look at some 2-by-2 examples. First example, let's say that our matrix A corresponds to 90-degree counterclockwise or anti-clockwise rotation. So we saw previously that the matrix for this was given by 0, 1, minus 1, 0. Now, the inverse to this is a clockwise rotation. So we're talking about transformations from R2 to R2 here. So a clockwise rotation is going to correspond to the matrix 0, minus 1, 1, 0. Where did I get that picture from? Where did I get those numbers from? Well, if we start with my two standard basis vectors like this, let's think about what happens when I do a 90-degree clockwise rotation. So we're rotating 90 degrees like this. So this one comes down to here, and this one comes over to here. So that's 1, 0, and that's minus, that's 0, minus 1. So the first vector, the standard basis vector along the x-axis, goes to 0, minus 1. That's the first column. And the second one goes to 1, 0. That's the second column. OK, so that's the inverse transformation. And let's check if we multiply these out, A times A inverse. So we get, for the first, the upper left component, 0 times 0 plus minus 1 times minus 1. I get a plus 1. I get, for the lower left, I get 0 times 1, and 0 times minus 1. So I get a 0. Upper right, I get 1 times 1, 0 times 0. Oh, wait, hold on a second. So I was doing the lower right. That's 1. And upper right, I get 0 times 1 and minus 1 times 0. There we go. So we got the identity matrix. OK, that's one example. Let's try another example. Let's think of what's called a shear transformation. So if I draw my xy axes here, let's suppose that the x vector, the x standard basis vector, stays exactly where it is, and the y vector is going to get pushed along to the side here to something like this at an x coordinate. That's the Greek letter delta there. So the transformation sends 1, 0 to 1, 0, and it sends 0, 1 to, we've now got the same height, but the x component is delta, so it's delta 1. So our matrix in this case is going to be 1, 0, delta 1. OK, so there's our matrix A. Now, the inverse, the transformation which undoes this, is going to be the shear in the opposite direction. So this shear took a box and turns it into a skewed box where the bottom is going to the left and the top is sliding to the right, and the middle stays exactly fixed. And so the inverse does the opposite. So it's going to take a unit box and shear it the other way. So now the bottom is going to slide to the right, and the top is going to slide to the left, like that, and the middle stays fixed again. And so now, if you do the same picture here, we'll get that we have to still fix the vector 1, 0. So this vector doesn't move. It's what's called a fixed point. And the vector 0, 1 now has to get sent to minus delta 1. So 1, 0 has to be sent to 1, 0. And 0, 1 has to be sent to minus delta 1. And so the inverse transformation in this case is 1, 0 minus delta 1. And if I multiply this matrix by this matrix, you can check, it'll work out. You get the identity matrix. OK, I've got enough space here to do the 2x2 general case. So the 2x2 general case is some completely arbitrary 2x2 matrix is A, B, C, D. And the inverse is going to be 1 over A, D minus B, C. So this is some scalar number in front times the matrix D, A, and I have minus B minus C. So you can take my word for it, or you can actually try to multiply these out and check, or ask the computer to do it for you, that this is indeed a formula for the inverse of this 2x2 matrix. Right. This coefficient in front here, this funny looking thing here, is what's called det of A. And that's the determinant of this 2x2 matrix. We'll talk more about determinants in the next video. for now, all you need to know is that it's some number that we produce by looking at the entries of this matrix A. Okay. In the next video, we'll learn all sorts more, probably more than you ever wanted to know about determinants, but that's enough for now. Thanks for listening. Right. Welcome, everyone. It's time to talk about determinants. So, first of all, if we have a 2x2 matrix, A, B, C, D, then last time I mentioned that associated to this matrix is a number called the determinant, which is A times D minus B times C. So we kind of cross multiply and get a number out. So we input a 2x2 matrix and we output a number. What's the geometric meaning? So let's think about what this matrix does to our standard unit vectors. So here's the vector 1, 0. Here's the vector 0, 1. This matrix will send the vector 1, 0 to that first column, AC. So let's suppose this is some vector here. And it sends the second unit vector to the vector BD. And now let me think about making a parallelogram out of these two and contrast that with the original unit square there. So the original pink or purple, whatever that looks like, unit square there had area 1. The area is exactly 1. The base has length 1, and the side has height 1. It's a square. Those are right angles, so 1 times 1 gives me 1. This green parallelogram, the image of that square, so this shape here the image of the square has some area. And if you do a little bit of trigonometry, you can work out that the area of this parallelogram is equal to exactly the determinant, AD minus BC. So the determinant tells us how areas get scaled. If this is true for this particular unit square, then it's true for any square at all, and therefore it's true for any shape that could be covered by taking a bunch of tiny little squares. So the determinant of A tells us how areas are scaled. So if I have some shape, I'll call it capital X, it has an area, then my linear transformation associated to this 2x2 matrix, I'll call that A there. This will be some new shape. And the area will be the area of X times the determinant of this matrix A. So in 2 dimensions, the determinant is telling us how areas are getting scaled. In 3 dimensions, there is a notion of determinant, and it does exactly the same thing. It tells us how now not areas, but volumes are getting scaled. because in 3 dimensions we should be measuring the volume of things rather than the area. And if you go to 4 dimensions and 5 dimensions and 6 dimensions, there's an analog, there's a notion of determinant in all these dimensions, and there's an analog of volume in all these dimensions, and the determinant tells us how these higher dimensional notions of volume are getting scaled. So that's geometrically what it means. Let's look at what this determinant thing actually is, though. So what is this determinant business? So it's a function, and the input is a square matrix of whatever size, n by n. So let's call this A, and I'll call the entries little a sub ij. This is the entry in row I and column j. So jth column and ith row. So the input is a matrix, and then we make a polynomial in all these aij's. So it's a some polynomial in all of the different entries of this matrix, and you evaluate that polynomial. And the output is a number. Now the bad news is this polynomial, if the matrix is big, this polynomial can be really huge. It's got a lot of terms, and the degree of the polynomial is n. So if you have a 10 by 10 matrix, this is a 10th degree polynomial, and it's going to have a lot of terms in it. But the good news is if you can manage to evaluate this and get this number, it tells you a lot about the matrix. The example was when we were looking at A, B, C, D. Then the determinant was equal to AD minus BC. So here, this is a 2 by 2 matrix, so we have a degree 2 polynomial function of the variable, of the entries. Right. So what are some of the properties? Well, the most important one, the reason that we usually care about the determinant, is the following. The determinant of A is non-zero if and only if this matrix is invertible, which was equivalent to lots of other things, such as the nullity was equal to 0, or the columns are linearly independent. And in fact, the columns would have to be a basis, or another one was the rank was equal to the dimension of the codomain, n. So this is what we call full rank. And another condition that was equivalent to this was the equation A times an unknown vector x equals some given vector v has a unique solution. And the unique solution was given by A inverse times the right-hand side vector v. All right, so A being invertible means we can find this inverse matrix, and A inverse times the vector v gives us the solution. So the determinant tells you whether or not you can find an inverse, and you can solve the system of equations. That's the most important property. Let's look at some other properties here that tell us how to compute it. So if we swap two rows or columns of the matrix A, so this is replacing A with some matrix, I'll call it A dash, A prime, then the determinant of this new matrix, where we've swapped either two rows or two columns, is equal to minus the determinant of the original matrix A. Third property is if we make a new matrix by multiplying some row or column by lambda, so we're multiplying either some row or some column by a scalar lambda, then the determinant changes by a factor of lambda. So the determinant of the new matrix is lambda times the determinant of the old matrix. So for example, if I have 1, 2, 3, 4, and let's take the determinant of this. The determinant is 1 times 4 minus 3 times 2, so that's 4 minus 6. I get a minus 2. If I multiply the first row by 2, I'm going to have 2, 6, 2, 4. So I've multiplied the first row by a factor of 2. Then the determinant is going to be 2 times 4 minus 6 times 2. So that's 8 minus 12. I get a minus 4. So I've gone from the first matrix to the second by multiplying by 2 on one row, and the determinant has gone multiplied by that same factor 2. One more property here. Property number 4 is if we add a multiple of one row or column to another, the determinant is unchanged. So in this case, what I mean by adding a multiple is I could say take the second row here and add to it, say, 1 times the first row. So I'd be looking at the matrix 1, 3. And in the second row, I'd have 2 plus 1. I'd have a 3. And 4 plus 3, I'd have a 7. And the determinant of this should be exactly the same, minus 2. So let's check. 1 times 7 minus 3 times 3, 7 minus 9 is indeed minus 2. Okay, so adding a multiple of one row to another doesn't change the determinant. So you can use that if you're trying to calculate a determinant by hand or write an algorithm. You can use this to simplify the matrix by doing these row operations or column operations, to simplify the matrix and get to a matrix where it's easier to calculate the determinant. And there is one last property I want to note here. I'll stick it over in this corner. Property 5 is if I have two matrices of the same size, the determinant of matrix A times matrix B is the determinant of matrix A times the determinant of matrix B. So determinant is multiplicative. It respects multiplication, but note that this is definitely not true for A plus B. So determinants are nice for matrix multiplications, but they're awful when you try to add matrices together. Okay, so 2 by 2 determinants, there's a nice simple formula. For 3 by 3 determinants, there's also a formula which is not too bad. So let's say the determinant of A, B, C, D, E, F, G, H, I. Here's some arbitrary 3 by 3 matrix. And we can work this out. This is going to be A, so I'm going to take this element here times the determinant of the complementary 2 by 2 matrix. So A times the determinant of E, F, H, I. And then I can choose to walk across this way, or I can do this vertically. I'm going to walk horizontally. So I'm going to alternate signs as I walk across. So I take minus b times the determinant of the complementary 2 by 2 matrix. So if I'm taking b, then the complementary 2 by 2 matrix is made out of these two and these two. I ignore the row and the column of the element b. And so I get b times the determinant of d, f, g, I. And then I keep on walking across, and I have plus, my sign alternates with each step. So now it's a plus sign, c times the determinant of the 2 by 2 matrix that's complementary to c. So if c is in the upper right, I take the lower left 2 by 2, and I have d, e, g, h. And we know the formulas for these 2 by 2 determinants. So this is the 3 by 3 case. And similarly, you can do 4 by 4 case, and we inductively define determinant for larger and larger matrices. So for 4 by 4, if we have the determinant of A, B, C, D, and so on, then this would be A times the determinant of the complementary matrix, which would be this 3 by 3 block, minus B times the determinant of the 3 by 3 block. So B times the 3 by 3 block, which is given by this column and these two columns, times B. And then I keep going, so it's a plus C times the determinant of the complementary 3 by 3 block. So C is there, and the complementary block is these two columns and this column. And the last one is C was a plus sign, so now it's a minus sign again, minus D times the determinant of the complementary 3 by 3 block. So the complementary 3 by 3 block for D was this block here. Okay, so that's a 4 by 4 determinant. And for 5 by 5 and bigger, exactly the same idea. So in general, we're going to walk across one row, alternating sign. And as we walk, each one of those is going to have a complementary n. So this is an n by n matrix. So each element along this row is going to have a complementary n minus 1 by n minus 1 block. And we do the first entry times the determinant of the complementary block minus the second entry times the determinant of its complementary block plus, minus, dot, 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 and so on. And this defines an n by n determinant in terms of the n minus 1 by n minus 1 determinants of various submatrices of this big matrix. And if you can define n by n matrices determinants, then inductively you define n plus 1 by n plus 1 determinants and so on. So on the one hand, this gives us a great definition. Mathematically, it makes sense, and it satisfies all those properties that I just listed on the previous board. The downside is this formula is very, very big and it takes an inordinate amount of time to compute as your matrices get larger and larger. When you get up to matrices of size 50 by 50 or 100 by 100, you're not going to be able to compute the determinant of these things, even if you have a supercomputer. So these determinants get very, very big, very, very fast, because there are just so many terms in them. And so a lot of computational linear algebra involves trying to find ways of getting at the inverse matrix or getting at the information that we want without having to compute determinant. A lot of the work we do in linear algebra is avoiding having to use determinants. But for theoretical purposes, it's good to know about them. So that's the end of the video. Thank you for listening.